Video about integration of x to the x, dx. We'll build a short lesson that explains what makes this integral special, and what we can still do when there isn't a simple antiderivative. Let's use a simple diagram to make the relationship easier to see. First, let's orient ourselves. We're trying to understand the area under the curve of x to the x, and also why finding an exact antiderivative is harder than it looks. We focus on positive x, so the expression stays real and well-behaved. A great teaching move is to rewrite x to the x into a form that calculus likes. Exponents become easier when we switch to the exponential function and natural log. This rewrite is the key, because it turns a tricky power into an exponential of something. Now, ask yourself, what would we normally hope for? We'd love the derivative of something simple to give us x to the x. So let's check the derivative of x to the x, because it tells us what patterns naturally appear. This extra factor shows up automatically, and it's exactly what makes the integral not match a simple guess. That little log plus 1 is a big deal. It means if we try the usual tricks, like reverse product rule or a quick substitution, we don't get a clean match. So for an indefinite integral, there is no elementary closed form in the usual functions. But that's not the end of the story. In a short video, a nice next step is to show a practical tool. Series. Since x to the x equals e to the x ln x, we can expand the exponential. Why does this help? Because integrating a sum term by term is often much easier than integrating the original complicated function. Each term becomes a power of x times a power of natural log of x. In a 3-minute lesson, you don't need the full general formula. It's more teaching-friendly to show the first few terms, so students see how an approximation antiderivative is built. These first terms already give a surprisingly good local approximation near x equals 1. Now we integrate those pieces. The first part is just x. The second part, x times natural log x, is a classic integration by parts example, because the log gets simpler when you differentiate it. Integration by parts is chosen because it trades the log for something simpler. So an easy takeaway is, we can build an approximate antiderivative by integrating a few series terms. That's often what we do in applied math, when a closed form doesn't exist. This symbol is the honest promise. We're getting a usable approximation, not a perfect elementary formula. To make the video feel complete, it's nice to include one beautiful exact result, but as a definite integral. On the interval from 0 to 1, the series method gives a famous alternating sum. Definite integrals are where this topic becomes especially elegant and meaningful. Finally, tell the student what they should do in practice. If you need a value, use numerical integration. If you need a formula, use a series approximation around the region you care about.